Hello. Thank you, Catuscia, for the introduction, and thank you, Griselda, for your laptop, without which I think this talk would have been difficult. Okay, so I'm excited to talk about our work on differentially private Oblivious RAM. This is joint work with my advisor Pratik and Paul Kaff, who was a former professor at Princeton. So, okay, expected pointer doesn't work. Sorry, I was using the wrong one. Okay, so what is an Oblivious RAM? So Oblivious RAM is a mechanism for a user to access data privately, but from a private database. So as you can see in this graphic, a user wishes to request a record R from a database, and the user gets back the record R. But the obliviousness or the security property which we are aiming for here is the adversary, in this case the database, should not know what item was requested or what record was requested. ORAMs typically are deployed in two contexts. So the first one is in a client-server environment where the client could be a smartphone application. The server or the database in this case is the client's Dropbox or Google Drive account, and he wishes to retrieve a record from that. The other application scenario for ORAM is in a trusted execution environment such as SGX-based enclave. In that, the last level cache tries to access items from the DRAM, which is untrusted. So what's the problem with conventional Oblivious RAM schemes? So if you look at how typical ORAM schemes work is you request a record, and what the ORAM scheme does is it makes a few fake requests on your behalf in some sense, and what this does is this increases the overhead of the scheme. Typical ORAM schemes incur logarithmic overhead for bandwidth and local storage, so that hinders their practical deployment. So the key insight which we introduce in this work is, can we improve performance by relaxing the privacy of these ORAMs? So thinking of statistically private ORAMs, we would like to have better performance at the cost of a privacy loss. But the important challenge here is, can we rigorously quantify such a privacy loss? And the second challenge is in terms of developing protocols which can actually take some of the privacy loss and translate them into performance benefits such as reducing the bandwidth or the local storage. Finally, we would like to achieve privacy proportional to the application resources. So for instance, if your application does not have enough bandwidth to run a full ORAM protocol, can you achieve maybe something like 50% privacy, but at the cost of a reduced overhead? So we solve the first challenge by using this notion of differential privacy. What we do is we introduce and formalize the concept of a differentially private ORAM. Now what this does is this gives a rigorous or formulation or mathematical framework to argue about statistically private ORAMs, which is ORAMs with reduced privacy. And then second, we introduce root ORAM, which is a family of statistically private ORAMs. In the second part of the talk, I will talk about root ORAM, which is this family of protocols. I'll give some theoretical and empirical results which talk about giving security guarantees about quantifying the privacy loss of these ORAMs, and also about the performance benefits we get on the other hand. And finally, I'll talk about an application of DP-ORAM which showcases the utility of that for the application of private information retrieval. So moving to differentially private ORAMs, this schematic sort of represents how a ORAM works. So on one hand, you have the program which gives the user an input access sequence. This input access sequence could be give me record 5, 10, and 20, for example. And then the ORAM protocol translates that into a series of requests to the untrusted memory, which in this case is server. The server is just going to act as a dumb mechanism which gives back whatever you request. So that's where the ORAM overhead is translating from A going to the output. And then the server gives back the requested records, and then the ORAM protocol gets back whatever was requested by the program. Now, what we have to note that ORAM mechanisms are statistical in nature, and so they are typically randomized, and so whatever input access sequence you have, you'll have a distribution on the output access sequence. So it's not one fixed output sequence, but it's a distribution. And then you have guarantees that this distribution should be just uniform, or it should look indistinguishable for any input sequence. in a differentially private ORAM, what we do is we consider this notion of neighboring access sequences. So you take in two input access sequences, A1 and A2, which differ in a single access. And then you study the effect of these differing access sequences on the output they produce. So more formally, if you look at this schematic, sorry, my slides go from one image to the next. That's how most of the talk is. But so if you look at this image, so the distribution of the output sequences on the input access sequence A1 is shown in red, and on A2 is shown in blue. And as you can see, the distributions are slightly different. And what we're really trying to capture is quantify the statistical closeness of these distributions, and that becomes your privacy metric, or that becomes your privacy loss. The smaller it is, the better privacy you have. So next I'll dive into the protocol construction. So this is the setup of root ORAM. On the server side, you have a number of binary trees. K is a parameter of the system, and for k equal to 1, you have two binary trees. Each binary tree, each node of the binary tree is called a bucket, and each one consists of multiple blocks, which is the smallest unit of data from the ORAM point of view. As you can see, the data items, at the client side, you have a mapping which is stored, where each data item is mapped to some leaf on the server side. Now let's take an example of what this mapping really means. So if we look at mapping, let's say data item 2 is mapped to leaf 1. What that means is we maintain this invariant throughout the protocol that the data item 2, if it is mapped to leaf 1, it will be found on the path from the leaf 1 all the way to the root, somewhere along the blocks in that. So let's see how ORAM access works. So when you access, you're going to you're going to ask from the server the whole path from the root to the leaf, and you're guaranteed by the invariant that you'll find your data item in there. So that's the RAM part of it. So the next step is you update the mapping. So you randomly assign the block 2 to a new leaf. So in this case, it was mapped to leaf 2. Now the key insight here is about this update mapping. So if you use a uniform update mapping, then it leads to a conventional ORAM security. But if you use a non-uniform mapping, you get a differentially private ORAM. So in our case, the mapping which we look at is a non-uniform one, where the currently mapped subtree has a higher probability than any other subtree. And what this does is it lowers the average placements of the block when they are written back, which improves the performance. On the other side, it results in a privacy loss because now data items don't move around as much. So let's just complete the protocol. So data item 2 was now mapped to leaf 2. So to maintain the invariant, we have to ensure that data item 2 is now placed somewhere along the path from leaf 2 all the way to the root. So what we do is we find the lowest common intersection of these two paths, which is, in this case, is marked by the arrow. And we try to place the block 2 in that location. So what we do is we take the item 2 from there and put it up in that the marked bucket. If you look at the whole protocol from the server's point of view, the server initial, so every time any data is written from the client to the server, it's encrypted with fresh randomness. So from the server's point of view, it sees a whole bunch of encrypted data blocks. And when it's read, it is going to give the client back one set of it. And when it gets back from client, it's going to get a new set of mapping. And so all it sees is the path to leaf 1 was accessed, and it was modified with something, but it doesn't see anything else. So I'll move on to the results. So first I'll showcase the theoretical results. So what we do is we show the above described protocol actually satisfies epsilon delta differential privacy for the following choice of epsilon and delta. This really shows that root ORAM is a differentially private ORAM for the following choice of parameters. The second result is an empirical one, where we showcase the performance improvements as a function of the security parameter. So on the x-axis, we have the security parameter. On the y, we have the improvement. And as you can see, the lower security you have, which is towards the right, the more performance improvement you get. The key takeaway from this would be DPORAM can be used to enhance at the cost of can be used to enhance the performance of a protocol at the cost of privacy. Finally, I'll talk about an application to private information retrieval. So PIR is a very closely linked primitive to ORAM. It's very similar to the setup in the sense a user wants to access data privately from a database, but except the difference is that the database is now public. So this could be a news website, it could be a US patent office where you wish to request a patent, or it could be, for example, PIR-TOR is a great example of a protocol which uses PIR to download TOR relays, TOR relay information. ORAM has been used previously to come up with PIR constructions. I've given 2 references down here. Typically how they work is you have a client who wishes to request a particular record R. What he does is he encrypts the client query to a trusted hardware on the server. The trusted hardware decrypts this query and then sends it to an ORAM protocol. The ORAM protocol then does the real working. It accesses the untrusted memory, it gets back the record, and then it gives it back to the trusted hardware, which then encrypts this response and gives it back to the client. So what we do here is, if this whole protocol becomes a PIR protocol, and if we replace the ORAM protocol with a differentially private ORAM, we showcase that this whole protocol becomes a differentially private PIR protocol, and the benefits of the differentially private ORAM protocol directly translate into benefits for a differentially private PIR protocol. So to see that, I have one quick slide on the comparison. So you can see here, the blue line is our differentially private based, differentially private ORAM based, differentially private PIR. And then these are state-of-the-art PIR protocols, DPPIR protocols. And as you can see, for any given value of the security parameter, if you consider the bandwidth which is required by the protocol, it's much, much lower. So DPORAMs can be used to give significant performance benefits for DPPIR. Finally, I'll conclude with just summarizing what I've talked about. So we first formalized the notion of a differentially private ORAM, which is the first one to talk about statistical ORAMs. We introduce a family of ORAM protocols and analyze their security and performance. Finally, we showcase the utility of DPORAM mechanisms in general for the application of private information retrieval. I would like to give one major takeaway from this talk is it's possible to enhance the performance of a lot of protocols by relaxing privacy, which we are seeing more and more in literature with differentially private multi-party computation, differentially private anonymous communication. And this is just one such work in the line. Finally, our source code is available at our group GitHub page, which is down here. And with that, I thank you for your attention and would be happy to take questions.
Thank you very much. Questions? Oh, lots of questions. Okay.
Hey, thanks. So when you described your root ORAM, you said the change you make is that leaves in the same tree are more likely than in other trees.
Yes.
But how is it even possible to put a leaf in another tree because you're not writing back to anything in another tree?
Yes, that's a good question because I haven't given the details, like the full details of the protocol in there. So at the client side, you also have, let me see if I have a backup slide on that.
Backup slides.
Yeah. So at the client side, you have something called a stash, which is also the case if you have too many elements in one bucket, you don't have space, then things go into the stash, which stay locally. And so now you also want to prove that the stash does not grow beyond control, and that's also what we do in our paper.
Is the stash a single stash for all the trees, or
Yes.
do you keep the single one for all
it's
the
the same
trees?
one.
Okay,
Yeah.
thanks.
Hello. Great talk. Cool direction for ORAMs, by the way. Could you speak a bit more about the K parameter that you used? Because you said something about having to replicate the trees with the K parameter, but I didn't quite understand where that was going.
Yes. The K parameter can be used. I mean, there are multiple ways. Like it affects it's called the bandwidth parameter because it directly affects the bandwidth of your protocol. And it also affects the amount of local storage you require. So it's I'll defer you to the paper, but like if you look at it, like there are basically theoretical results, like how much, if you change K, how much does the local stash change, and how much does your bandwidth get affected, and yeah, like actually, I might have a backup slide, but yeah, we can take it offline if you want.
Hey, thanks for the great talk. I was wondering if you can build the PIR scheme from ORAM without using trusted hardware.
Let's see. Now you're putting me on spot, but let me see. At least not that I can think of. I mean, ORAM schemes are sort of, if you see intrinsically, they require the client or like the user to have control or access of the database because encryption is like one big part of it. If you don't have trusted hardware, I see it hard to because PIR, the database has to be public. And so if you don't have some kind of, not a trust assumption, but some kind of advantage you have in there, like I don't see a way of just taking a ORAM and like using it for a PIR. Does that answer the question? No? Somewhat.
So I had a question, which was,
yes.
if I understood correctly, every ORAM access leaks a little bit of information. So that would mean that if you wanted to use an ORAM with some arbitrary program, maybe through a trusted execution environment, you have to think about how many RAM accesses it makes. Is that right?
Yes.
Okay.
So yeah, I think it has the same set of problems like differential privacy might have. You have to set a budget, you have to analyze how much each query requires, and then you have to set it appropriately so that you don't exceed the budget. We also have some results where, so this differentially private ORAMs are like, they have the same problem. So if your access sequence differ in too many elements, then it becomes, the privacy guarantees degrade, like not linearly, but there are results. And so what you have to do is either use this in, so this is not a silver bullet for like any kind of application, but if you look at specific applications, it might be good. So differentially private PIR is a great application because there the access sequence or like the secret just differs by one, because you have either you access this or that. And so that's one good use case, and then you can also mix it with, like, so for DPPIR, we have these results on the lines of Toledo and Goldberg's work, where if you use an anonymous communication system, you can improve the privacy bounds a lot more. And so you can use much more, many more, sort of for the same privacy budget, you can do a lot more accesses. Yeah.
Any other question?
There was one back there.
Oh.
So I was just skimming through your paper, and for the evaluations that you have, you use z equals 5. Mm-hmm. But I know for PathoRAM, for instance, if you use a smarter eviction strategy, like if you use reverse lexicographic eviction, you can make z as low as even 2. Would you still have an improvement over PathoRAM if you were to squeeze that down to 2?
Yes. So I think these are constant performance improvements, and if you actually look at that, so that's Gentry's work on ORAMs, and so PathoRAM itself can go as low as 4, but not below that experimentally, and Gentry's work can go as low as 2 with this deterministic eviction scheme. That's one of the future works which we have left, is to, because we can use the same techniques and apply to our work, and we can get benefits. Right now, it's going to be hard because we have a whole trade-off space, and so if you trade off your security for good enough performance, you can still beat those. But there'll definitely be points where they probably beat this scheme, and yeah, so that would be my answer.
Okay, thank you.
Okay, I think we should stop here.
Thank you.
Thank you very much. So there is a short break, and we'll resume in 15 minutes.